see it, and it's on the board.
Yeah.
Is that?
So he's become understanding light arrays. He'll pretty much clear a lot of things about light arrays and conventional systems. And we'll take a break, and then at 1:30, 1:50, advanced subwoofer systems tonight. So without much further ado, ladies and gentlemen, Mr. Tom Sawyer.
Hey.
Good afternoon. My name is Tony. Not Sir, not anybody else, just Tony. I'm going to go through some basic understanding of line arrays for the next 1.5 hours, and then, as quite what I said, at 1:50 this afternoon, I'll also be doing some training on advanced subwoofer systems, how to set up, how to tune, how to set up different subwoofer arrays. We'll look at that a bit later on. So we'll have a look at basic understanding of what exactly is a line array. When somebody tells you, I want a line array, what exactly does it mean? What exactly is the use? Is there a function? Is it the best sound system in the world? My answer is no, no, and no. I need a sound system to be loud. Let's put a line array. Wrong. You want it loud? Use a point source. Don't use line array. So we'll cover this and I'll explain to you what is going on. So, a little bit about myself. I've been in the industry 35 years. I have not touched a mixing console since it turned digital. I am a systems engineer. That means I design speaker systems, I tune speaker systems, I do not touch bands or mixing consoles. So I take care of the mathematical part of the sound system. So these are some people I've worked with. Yes, I've worked with AC/DC, I've worked with Metallica, I've worked with Andrea Bocelli, I've done EDC, I've done Tomorrowland. I am a systems engineer. And I live in the Philippines.
Yeah!
Okay. Everything with a line array, we have to go back to the basics. We go back to the understanding of sound waves and frequency. Everything derives from this. What we hear is a class of kinetic energy. It's called acoustic energy. Acoustic energy consists of a fluctuating wave of pressure of high compression and also through the mediums. A single complete cycle of acoustic pressure consists of 1/2 waves of high compression and followed by a cycle of refraction. That means a high fraction of compression and a low recovery of refraction. The rate of fluctuation is called frequency, or what we call cycles per second. So every frequency, what you know as hertz, is the amount of cycles per second. So we know that 20 kilohertz or 20,000 hertz is 20,000 cycles per second. Okay? So if we look at it, in order to be classified as sound, waves must fluctuate between the rate of 20 and 20,000 cycles per second, or 20 hertz and 20 kilohertz. Okay? So what is going on? This is exactly what I'm talking about. The whole cycle is one complete compression, refraction. The issue here is that if we do 6 cycles per second, it's 6 hertz. If we're doing 24 cycles per second, it's 20 hertz. Why do I tell you this? Because every calculation we do in a measurement sound system is done in frequency. We must look at the frequency before we look at the dimension. When we talk about this afternoon, we'll do subwoofers. We'll discuss about how to space your subwoofers based on frequency and not based on measurement. We'll do that a bit later this afternoon. Oops, wait. So, it's called a period. A complete cycle is called a period of time. Okay? How do we get to the cycles? How do we know what the frequency is? The problem in sound is that it's not consistent. Okay? We know that 20 hertz has got a sound wavelength of 17 meters. We know that 20 kilohertz that nobody in this room can hear, okay? One of you in this room can hear 20 kilohertz. Not one of you. Why? Because as we get older, your hearing automatically deteriorates. Unless you're 7 years old, you can probably hear 20 kilohertz. If you're above 7 years old, forget it. That's why today we use that cycle as an engineering frequency. Okay? The average age goes degradation as you get older. It's nothing to do with sound systems, it's just a human perception. As we get older, it's a perishable skill. Okay? But we can calculate the length. It's simple. Speed of sound divided by the frequency. This is very important because we need to understand what are the wavelengths we're dealing with. So what is the perfect line array? The most perfect line array would be one infinitely long and infinitely spaced at zero to each other. Okay? It would be the same as me as taking 1,000 15-inch woofers, stacking them on end, and we get close to a perfect line array. That's how long it would take. So it's very important to understand the sales versus the engineering. What is the perfect line array? The problem is we don't have one because we're not dealing with cylindrical waveforms. We have a problem. The problem is we have low frequency woofers from 18-inch to 6-inch woofers. We've got mid-band in multiple 2-way, 3-way, 4-way sound systems. Okay? All trying to find the best way to couple in the vertical plane. And that's one thing you will understand the line arrays. They're only dealing with one axis. That's the vertical plane. You will not see a single line array manufacturer looking at the horizontal image because that's the fixed point. We know what that is. So every calculation we do is targeted in the vertical plane. So this is what we have. We've got 18-inch to 21-inch subs, 24-inch, 32-inch subs, doesn't matter. Running from 30 hertz to 120, that's a bit high for a sub. 120 to 500 doing low mids. Okay? High mids would be 500 to 2K. And then of course 2K to 16K. I put 16K because that's probably where everybody today is listening or can hear on the average. If you're over the age of 50 like myself, you'd be lucky to get past 14.5 to 15 kilohertz. Sorry gentlemen or ladies, it's physics and it's human biology. So, what is the concept of a line array? The concept is very simple. It's relative to the spacing between each speaker. In the middle of one speaker and the middle of another speaker, it's that spacing between that speaker and this speaker. So, in reality, if I choose 100 hertz because it's a big wavelength, it's easy to fix. If I use the dimension from the center of this speaker to the center of that speaker, does it calculate as a line array if it's equal or less than the lowest bandpass frequency? That means if I have a double 18-inch sub, no matter if it's a sub or a top, you're still creating a vertical line array. And the spacing between the center of that one and the one above it is less than the dimension of its frequency, it works like a line array. The problem is low frequency is easy. Big wavelengths. 100 hertz has got 3.4 meter wavelength. 50 hertz, 6.8 meters. Okay? This is easy. The problem is when we get to the mids and the highs, this is where the problem happens. So as we get these speakers closer and closer together, here is 100 hertz at one wavelength, 3.4 meters. If I bring them closer, this is 1/2 wavelength. Let's bring them even closer. Now they're starting to act like a single identity. Let's get to quarter wavelengths. Those two sub-speakers become one speaker. That means we are getting line array behavior at that frequency and that frequency only. The closer we get the speakers together, the better it's going to be. On contrary to point source speakers. We were always taught that point source speakers, let's stack point source speakers this way. No. Why? It introduces cone filtering and wave interference. But in a line array, because you cannot hear the cone filtering in the vertical plane, your hearing doesn't hear it. But if I take that same speaker and move them horizontally, you will hear the cone filtering. Take that same speaker and move it this way, you don't hear the cone filtering. Because psychoacoustically, we have to understand how we hear something. I actually have a custom-built speaker. I hope it works. Okay, just show this in a bit more detail. So the low frequency is the easy part. Low frequency is simple. 100 hertz has got a wavelength of 3.4 meters. 1 kilohertz has got a 34 millimeter or 12 inches of wavelength. But the problem here is at 10 kilohertz. Your wavelength is 34 millimeters. Okay? That's it. That's the wavelength of 10 kilohertz. The wavelength of 100 hertz is from me to the camera. The wavelength of 20 hertz is from me to the back wall. But we still don't have speakers that can generate 20 cycles. So we're okay. See, I got the sound system 20 hertz, 20 kilohertz. There are no speakers that can do 20 hertz, and there are very, very few people that can do 20 kilohertz, especially for live sound. Okay? So besides the whole short wave, long wave thing, what else is there to think about? Woofers and compression drivers, even when loaded into a waveguide, naturally radiate sound in spherical waveforms. What does this mean? I'm not going to bore you with a bunch of physics. Okay, I'm going to try and simplify it for you to say, listen, I'm not going to give you a headache with a lot of Greek alpha. I'm not going to do that. I'm going to try and simplify it a little bit. So it's going to be a compromise between explaining the basics and a lot of high technical stuff. So I'm trying not to. I'm going to try and keep it as simple as possible. Let's take a look. Let's take a single component. If I drop a pebble into water, what happens? It's going to radiate away, and the waves are going to slowly get bigger as you get further away from the stone. Now, the theory is, as long as I drop another pebble within one wavelength of that stone, the waves will sound in the file. I did create a video clip for it. Okay. Please bear with me, I only finished this PowerPoint yesterday. Okay. Let's put a single, that's a single stone. Let's put a single stone in the pond. Okay, this is a sound wave coming out of a speaker. Okay? Now, if I don't have it spaced correctly, what's going to happen is we are going to create wave interference, one interacting with the other. Now, this is very dependent on frequency. So there's going to be different reactions from different frequencies. But what happens if I get these two close enough where they start to work together as one? If I put them within the same wavelength of each other, we can make sure that those two speakers are acting as one. But this is the problem. A line array could be acting as a line array in the low frequency because the wavelengths are long, but acting as a point source in the high frequency. So you've got to be careful here on how you look at it. So what do? So the idea is to change the natural radiation of high frequency devices. The problem is, if I ask you, how do you mount a high frequency into a speaker cabinet, you're going to tell me what? We'll put in a horn. Okay, we're going to stick it in a horn, and we're going to put point source out, the low frequencies are line rate, we're going to put a horn out in front. The problem is, if you look at the spacing between the two horn mounts, that's your limited line array frequency. We can't get them close enough, remember the wavelength thing? We can't get them close enough to act like one line array. So we've got a horn here, another horn here, the spacing is the limitation on the frequency. We can't get them close enough to be able to sum together to act like a line array. So, the easier way is to find a way of converting the horn-loaded sound into a plain wave. So, conventional horns have expanding waveforms propagating the boundaries of the horn. Why are there spherical waveforms coming out of a horn? Quite simple. The path length of the outer part of the horn is longer than the path length that's coming out of the center of the horn. So the center of the horn's going to come out first, and the rear end is going to come out, and it's creating spherical waveforms. The problem is, we need to get these speakers closer and closer together. You can't do with that, because the spacing is too high. So, if we look at line arrays, this is the interference period. Right? Okay. The practical upper limits summate with the horn mouth resulting in the circular segment, which is the interference. However, when you're dealing with line arrays, sorry the image is not so good, but it gives you a good idea. What we're trying to do is remove these spherical waveforms to create something that comes out and divides the sound so it comes out all together. And by splitting these signals, different brands have different ways of doing it. By splitting the sound up, now gives me a spacing of this much, not this much. By putting in the path length here, if you look at the path length here, it goes around, the path length is equal to all exits of the horn. So now makes each one of these segments an exit point. So it's the center of each segment and not the whole horn. So, if we look at the spacing center-center, that's 34 centimeters, that would be a line array up to 1 kilohertz. Okay? After 1K, forget it. However, I now have summation of the center to center is now 34 centimeters. I have a line array behavior up to 10 kilohertz. Different manufacturers have their own way of doing it. There is not one way to fix this. Every brand has got their own way of doing this. Okay? Are they all right? Are they all wrong? They're all right and they're all wrong. Nobody is, who's to say that they are? But listen, everybody has their own way of doing this. What they're doing is taking a horn and changing it from spherical waveforms to plane waves, and taking the horn mouth, which is like this, and giving multiple of path lengths so that the spacing is not the middle of the horn to the middle of the horn, it's now the segment in the HF section in the plane wave. But we have to consider the human element. The human element is also important. Okay? How do we hear sound? We don't hear cone filtering in the vertical. Oh, really? No, we don't. And I'll show you why we don't. We hear cone filtering. What is cone filtering? I hope we all know what cone filtering is, yeah? When two of the same frequency arrive at different times. Okay, good. The human element. Those gentlemen with nice big flappy ears, I congratulate you. You are fantastically good sound engineers. People, if you have small lobes, not so. Okay, these are your radars. The bigger your ears, the more frequency you can obtain. But the problem here is horizontal vertical discrepancy. People misunderstand that if I take a speaker and have a speaker in front of me, if I move a speaker 35 degrees off or 90 degrees off, my hearing is going to change. For those doing live sound, when you're doing a live sound, you have your main PA and you're putting delay towers, okay? And you're putting your delay lines and you're now going to time a line and you put a delay line 90 degrees to the main PA, you can't do that. Why? You cannot time a line sound at 90 degrees to each other. But you forgot, psychoacoustically, you're watching a stage there and there's sound coming from here. Your focus of attention must always be the stage. If you run a delay line, don't EQ those with a measurement. Those who use smart assist you and go, oh, on the scope it looks okay. No, because you're looking at this mathematically. You're not thinking about how we hear sound. If I move a speaker from there to there, I can gain up to 10 dB, which a scope does not see. So you must always EQ any off axis differently in the high mids. So we have horizontal discrimination. Vertical discrimination is simple. There is none. If I put a speaker there, I'm only indifferent. The only difference you have in the speakers in the ceiling is which is left and which is right. You can't stare at image anything above your head. But I'm going to try something. I've been working on this. It's been a toy I've been playing with and been using. I've just synced my phone to the amplifier. And I'm going to play some pink noise. What I'm going to do is I'm going to move the speaker around horizontally and I'm going to try and create cone filtering within the speaker. It's going to be pink noise. And then what I'm going to do is I'm going to take that speaker, turn it vertically, and then see if you can hear the cone filtering in the vertical. Okay? Wish me luck. Okay? Let's connect this. Not bad idea, that worked. The idea is you can hear cone filtering in the horizontal, but not in the vertical. That's why line arrays get away with an awful lot. Point sources never used to be able to get away with so much. Now, line arrays get away with a lot more we're dealing with. So, the horizontal vertical discrimination is here. When we're close to an array, if we've got a line array there, the reality is, okay, you are hearing the high frequency of only one or two speakers. So when I look at a long line array, it could be 20 boxes, it could be 10 boxes, it could be 8 boxes. But I am at this point hearing the HF of only one or two speakers. But I'm hearing the low frequency of all the speakers. Okay? That's why the line arrays depend on one thing, array length. Array length is critical. A short line array is not a line array. It's a screwed up point source that you have to treat like a point source. 3 boxes of line array, 4 boxes of line array is not a line array, because line arrays need one thing, array length. Because everything determines the array length. The far field determines the array length, which we'll look at as well. That's why we call ski, most manufacturers will use what we call ski hill tuning. Get that terminology off my lips. So when you look at a preset for a single box, everybody says, oh, but my sound system should be linear. No. Linearity sucks. Linearity sounds terrible. The system engineer will give you a linear sound system. Why? Because it gives the front of house engineer a blank canvas to play with. Okay? Most system engineers make one biggest flaw. They put a microphone at the front of house and do a monarchy system where the microphone's at the front of house and forget about the 5,000 people who have paid money to go to this concert. The front of house is the last guy that I ever think about. Why? He's the easiest one to fix. The audience, people who are paying, are the ones we have to consider as systems guys. I don't care about the FOH guy. He's easy to fix. Because whatever system I do, he's going to be 6 dB louder than everybody else. Because he has a summation of the left and the right PA. So he's going to be he's the only one getting stereo. So don't play stereo left, right. Forget it. It doesn't exist. PA left, PA right. Two separate PAs. No such thing as stereo and live sound. Why? I can sit over here and can I hear right PA? No. So why try to do any stereo imaging? It doesn't make any sense. There's no point. But why do brands EQ like this? Why? Because the more low frequency speakers you add to the line array, they will become line array like behavior in the low frequency. So as you add boxes, automatically it will raise the low frequency because they are the ones acting like line array frequencies. That's why manufacturers will use the ski hill tuning and have separate presets, whether it's 6 boxes, 10 boxes, or 12 boxes, to compensate for the low frequency summation in the line array. Okay? But most importantly, it's all dependent on the array length. The array length of a line array, outside shootout should be simple. The discrimination should be, okay, we have an array length of 3.5 meters. I don't care whether you use a 15-inch, an 8-inch, a 10-inch, 3.5 meter array lengths. Helps level the playing field a little bit. Not 8 boxes, because 8 boxes of 8, 8 boxes of 10, 8 boxes of 15, 8 boxes of 12 are very, very different. Why? Different array lengths. But if I had made simple terminology so that I can give you a 3.5 meter array length, I can put 16 8-inch versus 8 12-inch. More compression drivers, more HF. Better deviation. Remember, in a line array, adding boxes to your line array does not make it louder. Go from 4 boxes to 8 boxes does not make it louder. Gain in boxes mean gain in deviation, gain in control. We'll have a little look at that as well. Another myth that I like to talk about sometimes is the inverse square law. Simple mathematics, double the distance. Every time you double the distance, you minus 6 dB. Okay, for a point source, it's very simple. Every time you double the distance. So when we design sound systems, we don't look at the speaker. A couple of ratings that you don't need to waste your time with is peak power. That's just a number that is just done on the calculator and has no real value. Okay, the important ones are your continuous power rating and your 1 meter ratings. Peak power with every manufacturer is calculated. It's not tested, because they don't specify how much distortion is in the system. If I ask you, how much distortion is audible in your sound system? If you had to push distortion in your sound system, at what percentage point does it become audible? And the answer is simple, 1%. The human ear will understand 1% of distortion in your sound system. We'll actually come into this a bit later in the subwoofer training, which I will do with 150. Okay? Now the funny thing is, the inverse square law says that a line array is 3 dB doubling distance. This is a common misconception. because traditional line array theory anticipates that this is a cylindrical waveform of infinitely spaced, infinitely small devices, which is not realistic to today's solar system. The importance of distance. It is important when realizing considering line arrays to define the distance what is near field and what is far field. Okay? And this is a why near field to far field, because the theory says that a 3 dB per doubling distance in the near field and a 6 dB per doubling distance in the far field. Only in frequencies that are acting like a line array behavior. So you've got to be really tricky of how you play this. It's not something you use on a day-to-day usage, but it's good to understand. So the proposed inverse square law between the far field is 6 dB per doubling distance, in the near field is 3 dB. Again, only at frequencies that are acting like a line array, and in most of the ones we have outside, it's in the low frequency. But the problem is, the industry itself hasn't been able to make a decision on where people think the far field and the near field starts. Ergo, okay, Mark Weber decided that with not going to too far, dictates that the far field increases with the increase of frequency, also with the array length, which is what we've been saying from the get-go. The far field is array length dependent. What do you mean far field? The realistic distance a line array can throw. Please don't expect a double 8-inch line array to throw 50 meters. Don't, because it will do, but with what quality? Outdoors at the demonstration, there were baby line arrays hanging up there, and I went, the audience area is 50 to 40 meters. That's the extent of where a double 8-inch line array is going to go. Because with any tour, first delay line is no more than 70 meters from the pier. Your first line of defense is your first delay line, which is at 70 meters from your pier. We can, sure, we talk about array length. We can determine, okay, the vertical control frequency of a line array is dependent on the array length. Everything is relative to array length. So we have a 24-box array, in this case 8.6 meters long. We know we can look at a vertical control frequency of 191 hertz. The advantage of doing this, especially for tricky venues, is that we know we have vertical control over everything down to 191 hertz. The longer the array, the better the vertical control. Notice I'm only always talking about one thing, vertical. Never discuss the horizontal with a line array. Don't bother. No, we know it's a fixed point, 120 degrees, 100 degrees, or 90. We don't need to worry about that. But what's going on? We've got a line array on the top left at 500 hertz. It's starting to say, okay, this is 8-point-meter array. We know we have control. 500 hertz, we've got control. 250, we're starting to balloon at the top end of it. At 165, the top end of the array is almost blown out. Okay, so it's becoming an omnidirectional source by 125 hertz. All right, but array length. Don't come to me and sit there and say, I've got 4 boxes of line array, I want to make it work. You have 2 choices with short line arrays. Tonality versus linearity. You cannot make a linear sound system from a short array. So don't try to make a sound system sound linear. Don't try to do it and put 50 EQs in to try to make it work. If you have more than 4 EQ points in your sound system, something else is going wrong. Over-processing. Don't try it. I've seen people, actually 2 weeks ago, a line array, they EQ'd the bottom 2 boxes, the middle 2 boxes, the top 2 boxes independently from each other. I've seen some crazy stuff over the years. So the moral of the story is simple. With line arrays, keep it as long as possible. A smaller box but more of gives you better vertical control than a bigger box and small. I've had rental companies in Europe, some of them say we do nice big shows, but the big shows happen once a month, or once every 2 months, or once every 3 months. But the smaller shows, so buy a smaller box, and then add multiple of 20 boxes when you want to do a bigger show. So sometimes buying a big box doesn't always work. So the greater number of boxes that are used in an array is better. Light array behavior at low frequencies and greater directivity at lower frequencies. Improved long throw at lower frequencies. We will discuss at 150 or sometime when I've had a break, flying subwoofers. We'll be covering some of that as well in the next training session after this. So the advantages are, I would suggest if you're buying a line array, go with a smaller box and more of, rather than a bigger box and make it short. Why? Because you have better vertical directivity and deviation, what we call deviation. Deviation is if I have 4 boxes of line array and add 4 more boxes of line array, it does not make it louder. You don't get any additional power. What you gain is in deviation or control. That means somebody sitting here and somebody sitting at the back there are getting the same sensitivity. So gaining in boxes, you should gain in deviation, not gain in power. So what happens if you have a short array? What do you do? When you're mapping and you do your mapping, with those who have line arrays, who has line arrays in this? Who's used line arrays before? Anybody? Yes? No? Who's used line arrays here? Yes? No? No? Nobody's used line arrays in this place? Ah, yes, we do have somebody who's used line arrays. What happens when you have a short line array? And what do? Make sure those who do have line arrays, you are simulating more than one frequency. Simulating single frequencies doesn't help you. So when you're doing your mapping and you're doing your angles, your mechanical mapping, before you do your optimization, always look at multiple frequencies. Because what you see at 1K is going to be very different from what you see at 10K or above. Being relatively short, we only have line array control in the higher frequency bands, which means the lower frequency array behave much like a point source cabinet. So you need to be careful. Linearity versus tonality. At the end of the day, it has to sound right. And if you're trying to put a measurement microphone there, and you put a measurement microphone here, and trying to balance everything out, why? Just make it sound nice. And we say growing old gracefully. When you have a short line array, make it grow old gracefully. That means the further away you go away, make sure all the frequencies are summed together. Don't try to over-process your speaker systems. Okay? So, this is what you're looking at, the difference. Okay? On the box you have 4 boxes, and on the right you have 8 boxes. This is at 4 kilohertz. But now by mapping multiple frequencies, you get to see what's going on. Do we map with a single frequency and try to get it to work? Let's say this vocally, we're looking at 500 hertz to 4 kilohertz in the vocal range. Okay, let's map multiple frequencies. But then after 10 meters, your hi-hats have gone flat. You've lost your sibilance in your vocals. So when you're doing small arrays, small sound systems, try not to make it too linear. Try not to do your processing to make it look as flat as possible. Do the shortness of the array, try to make that, and just make sure the inverse kernel takes care of the slow rolling off at the back. It's a bit quiet at the back. You need more boxes to get more volume at the back. So the original example of an infinitely long device is to produce 20 hertz, 20 kilohertz. What does it similarly look like? It looks something like that. How are we on time, by the way? How are we on time? Okay? Unfortunately, it won't be practical. The moment that we start changing the layouts, it stops acting more and more like a line array. So whenever you add angles into your array, it's not practical for the seating area, but it actually, the more spacing in between you put boxes, it starts acting not like a line array. So solutions are simple. Another quick one is, I'll do this one quickly because time is short. Line arrays versus point source. Oh, I get this question a lot. Which one is better? Which one is it really cool? But we need to look at multiple things. Array length, HF compression driver. That's the key. I'll take a quick example. I've got a venue 50 meters. I've got a conventional point source system, line array with the same high frequency count, and line array with the same array length. Now, with this point source system, we have a total of 16 high frequency compression drivers. That's the one I'm interested in. I'm not too worried about the low frequency. But if you look at the deviation, 107 dB to 101 dB. Okay? Now let's add a line array with the same high frequency count. But look at the array weight, 1.37 tons. Okay? Let's look at a line array with the same high frequency count. 585 kilos. But the problem now is we still have 101 dB at the back, but we have lost 3 dB at the front. Okay? Moral of the story, if you want something loud and brutal, buy a point source. But if you want something with control, vertical control, you have a better using a line array. Now let's put something now with the same array length using a line array, and we actually gained in deviation. Again, not in power, didn't make it any louder, it just gained in coverage, in deviation. So the moral of the story is, the longer the array, the better the vertical control. If it's a short array, try not to treat it like too much like a line array. So in this case, that's what you're looking at in the HF increase count, but you didn't gain, you gained 2 dB. Just by adding an additional 4 boxes. You don't gain power by adding additional boxes into a line array, you gain in vertical control. The pros of a line array: high directivity in the vertical plane. That's important. Vertical plane. Less room citation. If you're doing an installation and you want the sound to be off the back wall, you can sort of tweak your arrays to be a bit different. With the point source, you don't have a lot of control. Smooth coverage, less deviation in larger areas, less interferences that you can hear. And of course, line array cons, you need a large quantity of speakers. They're also very expensive. You need to plan. For example, in the older days when I was doing large TV shows, there were things like, if you're doing churches, you have camera angles, they don't want speakers to be seen in camera angles, especially in the houses of worship or broadcast. You've got to be very careful. They don't want to see speakers in certain areas. So you've got to be really careful where you place stuff, and does that placement give you a problem for coverage? Of course, well, the only option of pro of the point source system is that it's loud. It's louder than a line array. And of course, most importantly, more efficient at short distances. Now, those who are using multiples of clusters, just a little wording on the easiest way is, please make sure you minimize the overlap between 5 and 10 degrees of overlap. With line arrays, you can actually end up shafted behind each other. You can actually do stuff which gives you around the edges, okay? Minimize the overlap between 5 and 10 degrees, because the 5 degree is, don't forget, the -6 dB point. So you must remember that you must always look the off-axis and on-axis measurements. When you do a loudspeaker measurement or you're doing a tuning of a PA, look at 2 measurements, on-axis and off-axis. You need to know what's going on both. Somebody asked me once how many measurement points do I take in a room? Depending on the room or the tour, but typically between 12 and 16 points. Because it is a law of averages. Okay? The more measurement points you back, the more information you have. And a good bit of advice, those who are measuring subs and tops, measure sub and top at the same point. So when you're measuring your 16 points of mid-high, take a sub count while you're there as well. Do we have time? Yeah? Okay. Column arrays. People say, oh, these column arrays, are they line arrays? Quick little understanding of what exactly they're dealing with. I see these column arrays in churches, and are they really line arrays? Let's have a quick look. It's a short paragraph, so let's have a quick look. We know that a steerable column array, the spacing between the drives is 10.48 centimeters, which is in a line array. Again, look at the driver spacing. Everything's relative to the driver spacing. 10.48 centimeters is 3.273 kilohertz. Okay? So anything from 3.273 and below, yes, it's going to work like a line array, which is what these items are defined for. These were decided as speech systems, so yes, they do work as line arrays in speech frequencies and below. Let's take a little look. If we look at a typical column steering array, we've got an array length of 99 centimeters. If we do some simple maths, the total array of the housing, okay, with line drivers, we know we have an effective line array control of 2 kilohertz, which is exactly what these things were designed to do, speech. Because at 2 kilohertz, that is the intelligibility speech measurement of 2 kilohertz. So we can take it a step further if we want to have a look at the array, and we can see as the array increases, as we increase the array dimension, so does the frequency control. So yes, they are in speech frequencies and below. The line array conclusions are simple. Okay, spacing between drivers in the vertical plane will determine the effectiveness of the vertical control of the line array. Longer arrays provide vertical control pattern. And of course, line arrays are not point and shoot. Okay? Line arrays are not point and shoot. Point to dead shoot, it's not a point source box. Yay! There we go. Woo. So, that's a lot of information. But the idea of thinking of simple things, important rules, when dealing with line arrays. Array length, smaller boxes is more efficient than having 3 or 4 big boxes. If you have a rental house, buy 10 or 12 double 8s rather than 4 double 12s. Why? You're going to get better control, better line array behavior in a longer line. And you still get the coverage you need. Okay? With a big line array, with big boxes, you'll get a very close proximity, big noise, but in the far field, it's going to die. But with a smaller box with more of, you have more vertical control as line array behavior. If you have a short line array, a 4 box is not really a true line array because it requires length. Treat it like a point source gather. So there are 10 degrees per box. You're looking at 4 boxes of 10 degrees, that's a 40-degree vertical coverage. That's not going to give you a lot to play with. Well, I'm going to take a few minute break, but I am doing another session shortly. Of this. I will be doing that shortly. Okay. It's about an hour. It'll be teaching you how to do cardioid end fire, flying subs, how to calculate vertical directivity of stacked subs. At what point does a sub, when it's stacked on the floor doing cardioid, does it become omnidirectional? So we will look at that and showing you how to calculate reference frequencies for that, and a little bit of basic information as well for left-right subs and center subs. And if I have time, I'll also show you some measurement tips on where to take measurement points and how to do measurement tips when calibrating your sound system. All right, so I need about, what time is it now?